So, we talked yesterday, no, Monday, about the conservation of total energy. And basically, we can look at this a couple different ways. If we have an isolated system, which means that there are no external forces, the only forces we have are gravity. There might be a spring force. There might be friction. Okay. Then we can say that the work is going to have to be equal to 0. But we're also saying that the work is equal to the change in the total energy. And this doesn't mean that the only systems this apply to is when an object is sitting still. Okay. We can apply this to systems that are in motion. We did apply it to that bear sliding down the pine tree yesterday, and the bear's kinetic energy changed and the bear's gravitational potential energy changed, and or not yesterday but Monday, and actually the bear's thermal energy changed. So we say that the energy can change form. Delta E mech is going to be delta K and delta UG and delta U spring, plus the change in thermal energy, which is going to be the work done by friction, plus any change in internal energy, which, as I said before, we don't really deal with. Okay, but it's up there in case you need it. Someday you may take PChem, physical chemistry, and that will be a part of your problem. And so you need to make sure that you have seen it. Okay. And so the problem that we did yesterday focused on looking at the change in the total energy being equal to 0. Sometimes as well, we say that the total energy at one point has to be equal to the total energy at another point. Okay, so you can do problems both ways. All right? So I encourage you to get the notes from Monday. If you were not here, I will try to post. I did record the lecture, and I'll try to post it on the portal. It just takes a long time for it to upload. Okay. All right. So let's apply this to a couple more problems. I think I've just got about 3. So let's start with page 206, number 53. If somebody would read it for us, please. You can read the whole thing. Okay. So let's draw a picture here. So here's going to be my spring at its natural length. So this part over here, as the problem tells us, is frictionless. Here's my block. It's moving that way. I'm going to let this, the relaxed length of the spring, be x equals 0, which I think kind of makes some sense. And the block is going to travel over here to x equals 7.8 meters, where it comes to a stop. But this part of the floor after the block leaves the spring has friction. And we're told that mu k is 0.25. Okay. Right? We good? Everybody got their picture? Okay. So what does part A ask us to find? Okay. So I'm basically looking for delta E thermal. And the book tells us that delta E thermal, which is equal to the work done by friction, is going to be that kinetic friction force times the distance. And in fact, I think, well, we'll do this. No, I'm going to do it. Makes me feel better. Okay. So what do I need to figure out here? I need my friction force. Okay. So what's the magnitude of my friction force? Okay, so it's going to be mu k times n, where n is the normal force. Because my block is just sitting here, what do I know that n is equal to? mg. Okay, so it's going to be, I need a better marker there. All right, we're applying Newton's second law in our heads, but we're right. Okay. But let's review for a minute. What does that dot product mean? It is a dot product. How do I rewrite that dot product? Okay, so Fk times d times cosine phi. And what is phi? Why don't you tell me what phi is in words first, and then we'll find a numerical value for it. The angle between Fk and d. Okay. Well, so if here's my block, and it's moving this way, so d is going to be over here. Which way is Fk? The other way, because the friction force always opposes the motion. So yes, that does tell us that phi is going to be 180 degrees. So cosine phi is -1, and I don't have to scream, which is always a good thing. Okay, so delta E thermal, FKD cosine phi. We know that the Fk is mu k times mg. I know what d is. Cosine of 180 degrees. And we can substitute our numbers in. So mu k was 0.25. What's the mass of the block? .5 kilograms. Acceleration due to gravity is 9.8 meters per second squared. What's d? 7.8 meters. And as we already said, the cosine of 180 is -1. So what do we get for delta E thermal? Really? Negative 60s? Okay, and we've really only got 2 sig figs, so that rounds to negative 67 joules. Okay. And one of the reasons why I don't like to do these problems using delta E thermal and delta E is that it gets kind of confusing what that negative sign means. I would rather do problems differently, and we'll do the next one the way I would rather do it. But the increase in thermal energy is going to be this 67 joules. Okay. All right, we good? Everybody got it? All right. Part B. What do we have to find in part B? Maximum kinetic energy of the block. What's up, Maddie? That's why I said I don't like the way that this works, because it has to do with the energy leaving the system. When I do the next problem, I think it will make more, I hope it'll make more sense. At least it'll give you another perspective. Yeah, it should bother you. Okay, so we have to find the maximum kinetic energy of the block. Where do you think this maximum kinetic energy is going to occur? Zoe. Okay, so the highest KE, or the maximum kinetic energy, is probably going to be there. We've taken all of the potential energy that was stored in the spring when it was compressed. We've turned it all into kinetic energy. There's no way for this block to get any more potential energy to turn into kinetic energy. It's just got this kinetic energy here, and then as it moves this way, it's slowly losing that kinetic energy to friction until it comes to a stop. Okay? Make sense? All right. So if we say that the change in mechanical energy plus that change in the thermal energy is going to be equal to 0, okay, and we're going to let the initial situation be when the block leaves the spring, and the final situation is going to be when the block comes to rest, okay, which were just the things that we talked about. Okay, we good? We got it? Yes? Okay, so remember that delta E max is really delta U plus delta K. Yeah, something with the signs is going to end up being screwed up. And that's why I hate this problem. All right, so delta U goes to 0, right? Because I don't have any change in potential energy. It's after the block has left the spring, so there's no change in spring energy. And there's no change in height, so there's not going to be a change in gravitational potential energy. Okay, so this basically tells me that the change in kinetic energy has to be the change in the negative of the thermal energy. Positive, yeah. Yep, I told you it's going to mess up the negative sign. I don't like, see, that's why doing it this way is so weird. I think what happened was back here, we shouldn't have done this, and we shouldn't have done that or that. We should have said that it was equal to that, and we should have just taken the magnitudes. And if we'd done that, then we wouldn't have had to worry about this, and that would have been positive. But that bothers me too. Yeah, exactly. And that bothers me too, which is why I like the way we're going to do the next problem better. Okay? So we're just going to have to wave our hands a little bit here. Okay? Which I don't like to do, but we're just going to have to do it. Okay? So delta K is going to be K final minus K initial minus delta E thermal. What's KF going to be? 0, because it's where my block comes to rest. So I'm going to end up with negative Ki is negative delta E thermal, or, and this makes sense, all of my kinetic energy became thermal energy. I can get rid of those negative signs. That makes sense, like thinking about the world. Okay. And if we ignore that negative sign from before, we can say that the maximum kinetic energy is 67 joules. And somebody who wasn't here is going to watch the notes and then come to me and say, where'd that negative sign go? And we'll go through it again. I know, but they're going to watch it and then they're going to say, where'd that negative sign come from or go? All right. There is one more part to this problem, part C. What does part C ask us? Okay, so what's the original compression distance of the spring? So if we go back to our picture here, at some point, the spring was compressed by some distance, I'm going to call it xi. And there was potential energy here. There was U spring, I. And where did that elastic potential energy go? It went into the kinetic energy of the block because this part was frictionless. Okay? As long as the spring was in contact with the block, there was no friction, so all of the stored energy in the spring became the initial kinetic energy of the block. So we can still look at this as a conservation of energy problem. It's just we can simplify it to a conservation of mechanical energy. Well, ultimately, I'm going to do that, okay? But it means that delta E mech is equal to 0. And I'm going to do this the way I like to do it, which is to say that the total energy when the spring is compressed is going to be equal to the total energy when the spring is relaxed, okay, which were the two situations that we talked about. So because it's mechanical energy, it's K initial plus U spring initial is K final plus U spring final. Okay, makes sense? All right. So anything up here I can cross off because it's equal to 0. What's one thing, Zoe? Okay, so K initial is going to be 0. Why? Starting from rest. Okay, anything else up here that we can set equal to 0? Maddie? Right, the final spring potential energy. Why? Okay, so when the spring is totally relaxed, it's at equilibrium. That's where we let x be equal to 0. So even if you want to look at the formula for spring potential energy, which is what? Yes, I am so not even going to acknowledge that. What's the formula for spring potential energy? Yes. Okay, so when we're talking about the final position of the spring, it's the relaxed length, so x is equal to 0. So this tells us that the potential energy of the spring is 1/2 xi squared, as we labeled on our picture, and that's going to be equal to whatever the kinetic energy was. And what is that kinetic energy? 67 joules. Okay, we've kind of changed around initial and final and stuff, but I think you guys can keep up. All right, and we've got 1/2. We know what K is. Somebody? What is 640 what? Newtons per meter times xi squared. So if you do the math, what do we get for xi? The problem told us that the spring constant was that. Really? What'd you get, Gianni? What'd you get? Did you take the square root of it? Yeah, I'm thinking that if you got the 0.5 thing, you didn't take the square root. Or something. And what should the units be? Meters. We're going to talk about those units for a minute. In a minute. That's what the answer is. So, my calculator people, I don't know. It does. Zoe, you're in the calculator seat. And you've actually handled it very well this year. I've been very impressed. But your own technical prowess has overcome the field for the most part. But you're tired today, so. All right, so let's talk about the units for a minute. I want to come back to this equation right here. All right, so I've got 1/2 k xi squared is going to be equal to the final kinetic energy. Okay, so let's just solve this for xi. So that's going to be 2 times kf divided by the spring constant, and then I'm going to take the square root, right? Do the algebra in your head? I'm not crazy. Okay, so what are my units for the final kinetic energy? Joules. What are my units for the spring constant? Newtons per meter. All right, so how do I get meters out of that? Yes, but we're not going to presume that that happens. Wait. What do you got, Casey? You had it. Okay. What did I tell you yesterday about how to remember what a joule is, though? Do you remember? It's everybody's favorite formula. What's kinetic energy? So this is a joule. I'm going to make it meters squared per second squared. Okay? If you can remember what the formula is, you can do the unit conversion. If you know what the units are, you might be able to get back to the formula. What's a Newton? Yeah. If you use F equals ma, newtons are going to be kilograms, meters per second, and that whole thing is going to be divided by meters. Okay. So, oh wait, it's meters squared because it's acceleration. Wait a minute, it's like something was going to be crazy there. So, my seconds squared cancel, which is beautiful. These meters cancel. My kilograms cancel, and what I end up with is the square root of meters squared, which is going to give me meters, which is what I want for a position, but it's also what the units work out to. Don't lose sight of that reality check, that consistency check. Okay? All right, we doing okay? All right, 2 more problems, and we'll take a break, and then we'll look at those AP problems before we move on. Okay? All right, so page 207, number 60. If somebody would read it for us, please. Okay, so does everybody understand what we're doing here? This is like taking a slide at the playground and pushing something up it, right? A toy or something. Take a stuffed animal. Does it go all the way up the slide? It's a long enough slide. So it'll go up part way and then it'll come back down, right? So if I have my slide or whatever it is, my incline, which has an angle of 30 degrees, and I've got some block that has some initial kinetic energy, and in fact, I think I'm going to make it a 1 instead of an I. That block is going to travel a certain distance along the incline, and then it's going to come to a stop after it's traveled some distance d along the incline. Now, what happened to all this kinetic energy that it started with? Some of it turned into thermal. What kind of potential? Gravitational potential energy. So what I have is an isolated system, because my only forces that are acting here are gravity and friction, and I know how to account for those. And so I can say that the total energy at position 1, which is the bottom of my incline over here, is equal to the total energy at position 2, which is where my block comes to rest. So what do I need to add to my picture if I'm going to talk about energy? Nope. Not if I'm going to talk about energy. Kinda. Where UG is equal to 0. Okay, so I'm going to let UG be equal to 0 at the bottom because Priya isn't here to choose some wacky thing that's going to mess us up. Okay, so I don't have springs. I only have gravitational potential energy to worry about, and I have kinetic energy. So I've got K1 plus UG1, and this is where it gets a little tricky. Is going to be equal to K2 plus UG2 plus E thermal. Because if I add it up, my kinetic, if this was a frictionless slide, all of the kinetic energy that I start with down here would become potential energy up here, right? Okay, if it was frictionless, but it's not. So some of that energy is going to be missing, and it's going to go into the thermal energy, which is why I put the thermal energy on that side of the equation. Okay, and we're going to end up taking an absolute value of it. All right. But you know that I like to go through and get rid of things that are going to be equal to 0, so I don't have to carry them around. So is there anything in that equation that's going to be equal to 0? Okay, so there's no gravitational potential energy at the bottom because that's where we let UG be equal to 0. Anything else? K2, because we come to a stop, that's the whole point, is that's as high as the block goes. So there isn't going to be any kinetic energy up there. So I've got K1, which I think I know, is going to be equal to UG2 plus whatever that energy is that I'm losing to friction. So let's see if we can do better with this one. What's my formula for gravitational potential energy? mgh. So I have to somehow have my height in here, right? Which is going to be different than d, but somehow, what? I can put it in terms of d because what do I have here? I have a right triangle, and I have an angle and the hypotenuse in one of the sides. Okay. So we'll keep that in our pockets for right now because we're going to need it later. Okay. But let's talk about that E thermal for a minute. What is E thermal really? It's not the friction force. It's related to the friction force. But what is E thermal? Yeah, but tell me what it is in words first. Where do you get that Fk.d from? It's the work done by the friction force. Okay? Now, of course, or maybe not of course, but when we look at this, the energy that's lost to friction, and I keep using that word, is lost. It becomes heat. It goes out into the environment. I can't roll back the film and recapture it like I can with other changes in energy. Okay, so this needs to be greater than 0 because even though I've lost it from my system, I need to add what its value is to this so that I have the energy that I started with. Okay? So what that means is I'm going to take the absolute value of the work done by friction. Okay? So what's the work done by friction? Okay, so it's going to be Fk.d or Fkd cosine phi And how do I write Fk? What? Well, no. It's going to be mu Kn times d cosine phi. That's the formula, is mu Kn. And when we did the last problem, I specifically wrote it, well, we specifically talked about what n was going to be, and part of that conversation was that my object was on a nice horizontal surface. So that yes, in fact, the normal force was equal to the gravitational force. Is that what I have here? No. So what am I going to need to do? So before I can apply F net equals ma, what do I have to do? Make a free body diagram. So here's my block sitting on my incline. What are the forces on my block? Okay, how does gravity point? Straight down. What else do I have? And which way does my normal force point? Perpendicular to the interface. And what else do I have? And which way does my friction force point? Opposite the motion, so for right now, down the incline. What's missing from my picture? Axes. I'm going to make that, here's theta too for whoever wanted theta. I'm going to orient my axes so that the x-axis is parallel to the incline, because that means that n is going to be in the y direction and I don't have to break it into components, and that's really what I want to solve for. But what force am I going to need to break into components? Fg. So here's going to be my Fgy. So if we do what Zoe talked about, which was F net, in this case in the y direction, is going to be may. What are my forces in the y direction? Fgy, and what was it? N. And what's my acceleration in the y direction? 0. Fgy, positive or negative? Normal, positive or negative? So my normal force is not going to be mg, it's going to be Fgy, which I now have to figure out. Okay. I always have to figure it out. So here's my triangle, which means that this is what? So this is theta. It's going to be mg cosine theta, because it'll be adjacent over hypotenuse. Okay. And we've talked about this before, about always figuring it out and not memorizing it because it's crazy. All right. Everybody got what they need? All right, so let's go back to that energy equation. So I had that K1, which I believe is something that I know, was mgh plus the absolute value of the work done by friction. And what am I trying to solve for here? D, okay? So I need to have H in terms of D, and we had that little trig relationship that we put in our pockets earlier. So if you solve that trig relationship for H, what do you get? So d sine, I think it's 30, right? Okay. And then what's my formula going to be for the work? Cosine 30d cosine 180. But I'm going to take the absolute value of that, right? Because that's the whole point of work, is it's a force acting over a distance. Okay. All right. So, again, K1, mgd sine 30 plus mu k mgd cosine 30. $1,000,000 question, what's the cosine of 180? -1. Okay, so if I ignore that, then I have a positive value for the thermal energy, which is what I want. Because what I'm doing is I'm taking all the different kinds of energy that I have at the end and I'm adding them together. Yep, we're looking for D. I can factor D out. Okay, so K1, which I think I know, I can pull out my D. So I've got mg sine 30 plus mu k mg cosine 30 and then D is going to be K1, which is some number, over mg sine 30 plus mu k mg cosine 30. I'm not writing out all the values this time, but you tell me what the answer is going to be. We have 2 sig figs, 4.3 what? Unit? Should be meters. We won't go through the units this time. What did others get? Okay, that's what I get as well. Okay. We good? So this is another way to solve them. Like I said, I prefer to do it this way. I think there will be some places in your homework where this might work more easily. Okay, and I have one more problem I want to do, but this one's kind of quick. Okay, and then we'll take a little break. All right, so page 207, number 65. If someone would read it for us, please. Okay, so let's look at that figure for a minute. So I have my curve, okay? The flat part here has friction, and it has a length L, which I don't really care about. And my particle starts up here at point A, which is at some height h is equal to L over 2. So what's going to happen? Talk me through this using energy words. And well, now hang on. So what kind of energy does it have up here at point A? Gravitational potential energy. Okay. So it's going to be converted into kinetic energy. And then what's going to happen? There's going to be friction. So what's going to happen to that kinetic energy as it slides across? Into what, Maddie? Yes. So some, we don't know how much, of that kinetic energy is going to turn into thermal. Let's assume for the minute it's not all of it. So by the time it gets to the end of the flat part, now what's going to happen? It's going to go up, and it's going to do what energy-wise? Convert the kinetic into potential. If we call this, for whatever reason, point B, is point B going to be as high as point A? No, because I've lost some of that kinetic energy to thermal energy. So I have less kinetic energy over here to convert into gravitational potential energy. And then what's going to happen? It's going to go back. But what can you tell me about the kinetic energy here and the potential energy at B? Those are going to be equal because there's no friction. So I've converted all of the gravitational potential energy at B back to the same amount of kinetic energy here. And then what happens is the particle crosses L again. It slows down. Kinetic energy is converted into thermal energy. What happens when I get to this end of the track? Not necessarily. Let's pretend there's still kinetic energy. Okay, so whatever kinetic energy is left here is going to be converted into potential energy. We'll call that point C. What can you tell me about the gravitational potential energy at point C and the gravitational potential energy at point B? Yeah, the gravitational potential energy at C is smaller because, again, the block lost some of that kinetic energy to thermal energy due to that friction force as it crossed the flat part of the track. Can you figure out how much energy it loses to thermal energy when it makes a full trip across the track? We could. Okay. So I think that the first question is, what's that energy? And how many trips can it make? Right? Because I don't care what happens at the end. That's just converting all of the kinetic into all of the potential, and then all of the potential back into all of the kinetic, right? I don't lose any energy there. I want to know how much of that initial potential energy at A is converted into thermal, and how many trips can I make, right? Yes, how many L's will it take to convert all of the potential energy into thermal energy? Okay, but let's look at one trip. okay? So 1 trip across L, that thermal energy is going to be equal to what? And we're talking magnitudes here. Remember, what is thermal energy? The work done by friction. What's my formula for work? No. What is it, Sari? F dot D. Okay. I'm only worried about the magnitude. So I've got my Fk, whatever my friction force is, and if it's 1 trip across L, what's D going to be? L. So that's going to be how much energy we lose in 1 trip. What's my formula for Fk? No. Mu Kn. I don't know where that's coming from, Maddie. We're going to ask ourselves again, what's N going to be equal to when my block is here? Now it's going to be equal to mg, okay? Here's N, here's Fg, no incline, no other forces, okay? But you have to ask yourself that question every time. Okay, so every E thermal, every time we make a complete trip, we're going to lose this much energy. So I'm going to say that Ug at the top, I need a letter for this. I've used X, is going to be X number of E thermals, right? And X is the number of trips that we make. Okay. On the first trip, I lose mu K mgl. On the second trip, I lose that much. So I've got Ug top, which is actually, I know what that is, right? What's mu G top? Or what? Or A? I don't even need to know what L is. I don't know why they tell you what L is. I don't need it. That. Yep. Okay, so I've got mgl over 2. X is just my number of trips. And then I had mu K mgl is the amount of energy I lose on 1 trip. And I'm solving for X, the number of trips I'm going to make. And it can be a fraction, right? A decimal. So what can I do here? Okay, so I've got my mg's, cancel my l's. So I've got x, which is my number of trips, times mu k, I've got 2 equal signs there, is equal to half. Right? So x is going to be 1 over 2 mu k. I think mu k was 0.2. So that's going to be 1 over 0.4. What's point? No calculator. Freeze those fingers, Gianni. What's 0.4 as a fraction? 4/10 or 2/5. So what's x equal to? Halves, or as a decimal, because you can do that in your head, 2.5. So it makes 2.5 trips. Someday the zombie apocalypse will come and you will have to do math in your head. So don't forget how. It doesn't matter. Do the math in your head. So what's going to happen is my block starts up here. It makes one trip, goes up here, makes another trip, comes to point C, and then it gets halfway across. I don't care. Oh, all right. Then yes, 20 centimeters. Okay? All right, so we're going to stop this here.